Welcome to BJT universal bias with a decoupling resistor. So here's our variation of the universal bias circuit with the R1 decoupling resistor. And typically you would see this schematic or this type of biasing in the first stage of a multi-stage amplifier. And we're going to get started the same way that we did basically on all of these biasing circuits. We're going to write our Kirchhoff loop equations. And just like the other universal bias circuit, we're going to need two of them so that we can do simultaneous linear equations to solve for two variables. So we need to write our two equations, and they're very similar. We're just going to start at minus VCC. We're going to go through VR1, VR2, VBE, VRE, and that completes the first loop. All that should be equal to 0. The second loop is very similar, but instead of going through VBE, we're just going to go straight through VR3. And that gives us our two loops. And just like on all these biasing circuits, we're now going to get our Kirchhoff voltage loop equation in terms of current and resistance. And you can see this at the bottom of the screen here. We're starting to flesh out these formulas. So now we've got our two formulas, and we've got it in terms of IR1, IR2, IE, and IR3. So we need to make some, we know we can get IE in terms of IB, but we need to take a look at IR1, IR2, and IR3. So Kirchhoff's current law, we know that IR1, we can take a look at the schematic, and we know that IR1 is equal to IR2 plus IC. We also know by looking at the schematic that IR3 should be equal to IR2 minus IB. So now we can substitute in for IR1, IR2 plus IC in the equations, and for IR3 we can substitute in IR2 minus IB. So now we've got our two formulas, and we're going to distribute and kind of clean everything up and get everything into individual terms across the equation. And we can see that we've got an IC and an IE floating around, and it looks like we've pretty much got IR2. And so we're going to clean up these equations and get everything in terms of IR2 and IB. You can see all the math on this page. So now we've got our final two loop equations in terms of IR2 and IB. And so at this point, this is where I'd pull out the old TI-89 and punch it right into my simultaneous linear equation solver and solve for IR2 and IB. Now that we have IB, we can easily find IC and IE, find all of those voltages. Remember IR1 is equal to IR2 plus IC. Find that voltage. Now, we've got our VCE and our IC, but we need to take a real close look at our VCE cutoff for this circuit because it's not going to be equal to VCC. So we know at cutoff our transistor is acting like an open. So there's no current flowing through the RC/RE branch of the circuit. So now we see that we've basically got an R1 plus R2 plus R3, VR1, VR2, VR3. We've got a voltage divider here because R1 is going to drop some voltage. And so we can take our VCC divided by that, find the total current through that branch, and our RC/RE branch should be dropping the equivalent because it's in parallel with the VR2 plus VR3. And we know that there's no current flowing in that branch, so therefore our VCE should be equal to the VR2 plus VR3 in cutoff. Now saturation, we're going to look at it exactly like we've been doing before. We're going to treat that transistor like it's a short. Now as long as your IR3 is at least 10 times greater than your IB, we can just treat the transistor like a short and put the RC plus RE in parallel with the R2 plus R3 branch. Find an equivalent resistance for that, add that to R1, and then divide that into VCC. That gives us our total current when the transistor is saturated. Now we multiply that current by R1, that gives us the voltage R1. Take that voltage and subtract it from our VCC, that gives us the voltage that's across our parallel branch there. And we know that the transistor is acting like a short, so if we take that voltage and divide it by RC plus RE, that will give us our maximum current through that branch when the transistor is shorted.